Hi everyone, hope you all are doing good. This is Suresh, lecturer in chemistry in Chambers Degree and PG College, Palakollu. Right now the most important thing is just come out of the situation, be safe, keep others also safe. That is most important thing. Exams and other things can be done later also. Okay, just try to take this thing in a positive way. And this does not mean that you will stop studying. So keep studying, keep learning. So in this session I would like to start final B.SC 5th semester. 5th paper, 1st unit, coordination, chemistry. Okay, so before discussing coordination chemistry, what are coordination compounds, you have to understand addition or molecular compounds. What are addition or molecular compounds? The solutions of two solutions of stable salts are mixed together in a specific molecular composition which gives new compounds. Those are called additional molecular compounds. Okay, I repeat it again. When solutions of two stable salts are mixed together in a molecular proportion which gives new compounds, those are called additional molecular compounds. So basically these compounds are two types: double salts, complex compounds. Okay, so what are double salts? The compounds which lose their identity in aqueous solution when it is dissolved in the aqueous solution. So what are double salts? The compounds which lose their identity when it is dissolved in the aqueous solution. For example, let's understand with the example: KCl, MgCl2, 6H2O. So this is known as a carnallite. KCl, MgCl2, 6H2O. So when carnallite dissolved in aqueous solution, which gives K plus Cl minus Mg2 plus ions. Okay, that means which lose their identity. It's dissociate in the solution. So which lose their identity. That means the solution of this compound which gives positive test for potassium, chlorine, and magnesium. Right? Let's take another example. More salt. FeSO4, NH4 twice, SO4, 6H2O. When more salt dissolved in aqueous solution which gives Fe2 plus SO4 2 minus and NH4 plus ammonium. That means the solution of this more salt which gives positive test for Fe2 plus SO4 2 minus NH4 plus, because they are available in the free state, they are available in ionic state. That's why which gives their corresponding tests in the solution. Potash alum. And the next example is potash alum. So K2SO4, Al2 SO4 thrice 24 H2O. So this is potash alum. So when this potash alum dissolved in aqueous solution which gives K plus SO4 2 minus and Al 3 plus. So all these are examples for double salts. What are double salts? The compounds which lose their identity when it is dissolved in the aqueous solution. Now coming to complex compounds. So what are complex compounds? Exactly opposite of double salts. So these compounds are lose their identity in aqueous solution. These compounds are which doesn't lose their identity in aqueous solution. That means so these compounds doesn't lose their identity when it is dissolved in the aqueous solution. Example, let us take example Cu NH4 NH3 4 times SO4. Okay, so this compound is formed by the combination of copper sulfate and ammonium. Copper sulfate, ammonium, that is the molecular addition compounds. This compound is formed by the copper sulfate and ammonium. So which can be formulated as CuNH4 4 times NSO. This is called complex compound. So here this part, so right hand part SO4 2 minus, so this part will get ionized, but this part will not get ionized, so which doesn't lose their iron. That means here this complex, the solution of this complex which doesn't give copper 2 plus test because it is not available as Cu2 plus in the solution. Okay, that means it doesn't lose their identity in the aqueous solution. Here we have to know few terms regarding this complex compounds. Okay, so in this chapter we are briefly discussing about what are complex compounds, what are the different theories to explain complex compounds, and isomerism complex compounds, coordination compounds, all these things you can here learn in this chapter. Okay, right. So here we can understand a few terms. So that is M, L, for example, N, Z, X plus M. So the basic structure of a complex compound. Here M is center metal atom. So this belongs to transition element, D block element. Okay, because why? So maximum D block elements are forms complex compounds. Why? Because D block elements are having vacant empty orbitals. Okay, vacant empty D orbitals. So here L is ligand. Ligand. So what are ligand? Ligand. What are ligands? So those are having lone pair of electrons which are available to donate this lone pair of electrons and forming coordinate bond with the center metal atom. So those are called ligands, right? And here Z. So here it is this square bracket is called as a coordination sphere. Coordination sphere. And here this part is ionization sphere. Okay, so in solution this part will get ionized. Okay, and this part will not get ionized, which is in the square bracket. So the whatever it is in square bracket, they are not in the ionic form. Okay, they are not ionized, and the whole here this is charge. So the coordination sphere, right? And here N is the coordination number. Coordination number. So how many number of ligands here? That is N ligands. That is coordination, that represents a coordination number. So what is the exact definition of coordination number? Is number of donor sites available, number of donor sites available in the ligand. That is number of donor sites of ligand which are coordinated with metal. So that is coordination number, right? Next, we have to assign the IUPAC nomenclature for this coordination component. So before discussing IUPAC nomenclature rules, we have to know few things. So nature of ligands, right? First, so ligands could be anionic, cationic, neutral. If you are having negative charge over the molecule or atom, that is your anionic ligands. If you are having positive charge over the molecule, that is cationic. If you are not having any charge over the molecule, that is neutral molecule. I will give you a few lists so that you can understand very easily. So that is first anionic, that is negative ions, negative ligands or anionic ligands. They are having negative charge over the molecule, right? Example, halogens, fluorine, chlorine, bromine, iodine, F minus, Br minus, Cl minus, okay, I minus, hydroxide, OH minus, Cn minus, SO4 2 minus, okay, H minus, hydride, and C2O4 2 minus, oxalate ion, and NH2 minus, amide, NH. If you remove one more hydrogen, that is imido. This is amido, this is imido, right? And oxygen. So O2 minus oxo, O2 minus superoxo, O2 2 minus, that is peroxo. Okay, so here fluoro. So actually the name ending, the anion ligands, the name ending fluoride, bromide, chloride, iodide, hydroxide, cyanide, sulfide. Okay, so the name ending with alphabet letter E, ending with E. So you just replace E with O. So while naming the nomenclature, you just replace E with O. That means this becomes fluorido, fluoro. Both will be correct. Fluorido or fluoro. That means fluoro, bromo, chloro, ido, hydroxo, cyano, sulfato, hydrado, oxalato, amido, imido, oxo, superoxo, peroxo. Okay, right. So these are the anion ligands. Next, neutral ligands. If you are not having any charge over the molecule, that means CO, you are not having any charge over the molecule. So this is neutral. This is carbonyl. So carbonyl, H2O, aqua, right? And CS, thiocarbonyl, and NH3, amine, PPH3, triphenyl phosphine, PY, pyridine. Okay, right. So there are some neutral ligands and positive ligands or cationic ligands. Cationic ligands or positive ligands. Right? That means over the molecule you are having positive charge. For example, NO plus nitrosonium, so ending with IUM. If you are having negative charge ligands, ending with O, that is fluoro, chloro, bromo, ending with O. If you are having cation over the molecule, if you are having a positive charge ending with IUM, right? That is nitrosonium. If you are not having any charge, for example, that is neutral, that is nitrosyl. So over the molecule, over the NO molecule, you are not having any charge, that is nitrosyl, neutral molecule. If you are having positive charge over the molecule, so that name becomes nitrosonium, right? NH2 actually, NH2, that is hydrogen. If you are having positive charge over the molecule, NH3, so hydrogenium, right? So these are the few ligands coordinating with the metal atoms, right? Next, so this is the classification of ligands based on over the charge, right? So all these things you have to write. So watching videos is not enough, you need to practice. Okay. So you have to maintain one running notes. So you have to write all the important things which are helpful a lot while preparing the notes, while preparing examinations, right? Next, denticity. The term denticity. So what is denticity? So denticity. So dentate, that is tooth. Okay, how many donor sites available? So here this can classify as monodentate. Monodentate. So what is monodentate? Monodentate. That means here having one donor site. The ligands which are having one donor site, which is coordinated with the metal atom with one donor site. So that is monodentate ligand. So what are monodentate ligands? The ligands which are having only one donor site. The ligand which is coordinated with the metal atom with one donor site. So at a time it donating one lone pair of electrons to the central atom, right? And next, bidentate. So bidentate ligands. So bidentate ligands. So bidentate ligands, tridentate ligands, tetradentate ligands, all these are polydentate ligands. Which are donating more than one lone pair of electron. If it is donating two lone pair of electrons, that is your bidentate ligand. If donating three lone pair of electron at a time, that means it having three donor sites, right? So that is a tridentate ligand. If you are having four donor sites, that is a tetradentate ligand. So a few minutes ago, I am giving few lists. Fluorine, chlorine, bromine, iodine, and carbonyl, pyridine. So all these are your bidentate, all these are monodentate ligands which are donating only one lone pair of electrons to the central atom, except oxalate. Oxalate is a bidentate ligand, right? So here examples for bidentate ligands. So which are having two lone pair of electrons, which are having two donor sites. Example, ethylene diamine. Ethylene diamine, which is represented by the En. So let's see the structure: NH2, CH2, CH2, NH2. Here two lone pair of electrons over the nitrogen. So these two are the donor sites. So this ethylene diamine donates two lone pair of electrons which are present on nitrogen. So coordinate with so these two are coordinate with the metal atoms. So two donor sites. So that's why this is a bidentate ligand, right? So this is there having any charge over the molecule? No. So it is a neutral bidentate ligand. If you see the anionic bidentate ligand, that is oxalate, C double bond O, O minus. Here oxygen having one lone pair of electron, here oxygen having one lone pair of electron. So these two are coordinated with the metal atom. So these two are coordinated with the metal atom. So this is a anionic bidental ligand. So because oxide having a 2 donor sites na, so it is a bidental ligand. In the same way, glycine, that is the NH2, CH2, C double bond O minus. Here nitrogen having 1 lone pair of electron and oxygen having 1 lone pair of electron. So these two are donated to the central atom. So all these are examples for bidental ligands. If we see like tridental ligands, that means so tri means 3. So at a time it donates 3 lone pair of electrons to the central atom, 3 lone pair of electrons to the central atom, right? NH2, let's take an example, NH2, CH2, CH2, NH, CH2, CH2, NH2. So this is CH2, CH2. So that is ethylene. So this is diethylene, CH2, 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 CH2. So diethylene triamine, 1, 2, 3. So here you are having 3 nitrogens na. So over the 3 nitrogens you are having 3 lone pair of electrons. So these 3 nitrogen donating 3 lone pair of electrons to the central atom and forming coordinate bond. So here this is tridental. So tetradental, just if you can extend this chain, you can get tetradental ligand. That means NH2, CH2, CH2, NH, CH2, CH2, NH, CH2, CH2, NH2. So there you are having 4 nitrogens. So 4 nitrogen having 4 lone pair of electrons. So they donate 4 lone pair of electrons to the central atom. That is a tetradental ligand. So this is diethylene. This is diene. So diene example for trident, tetradental triene, right? So this is classification of ligands based upon number of donor sites, right? So one more term, that is ambidentate ligands. Ambidentate ligands. So what are ambidentate ligands? Ambidentate ligands. So the ligands which are having more than 1 donor size. So more than 1 donor size. So that is monodentate ligand. It donates at a time 1 lone pair of electron, but they are having more than 1 donor site. Example, cyanide, CN. So carbon having 1 lone pair of electron and nitrogen having 1 lone pair of electron. Carbon having 1 lone pair of electron, nitrogen having 1 lone pair of electron. Either carbon donates or nitrogen donates, but at a time 1 lone pair of electron donates, either carbon or nitrogen, right? If carbon donates its lone pair of electrons to the central atom and forming coordinate bond. So then this ligand is written as Cn minus. Over the Cn you are having negative charge, Cn, and it is called as cyano in the nomenclature. If nitrogen donates its lone pair of electrons, to the central metal atom and forming coordinate bond, right? So that is isocyano. Understand? So here more than 1 donor site. Carbon is donor site and nitrogen also donor site, right? So either carbon donates or nitrogen donates. So if carbon donates its lone pair of electrons to the central atom, that is represented as written as cyano, and it is called written as cyano in the nomenclature. If NC, if nitrogen donates its lone pair of electrons to the central atom and forming coordinate bond, so it can be written as NC and it is called as isocyano, right? Let's take another example, NO2, that is nitro. If nitrogen donates its lone pair of electron, here nitrogen having 1 lone pair of electron, oxygen having 1 lone pair of electron. Okay, nitro, N, double bond O, single bond O. So O minus and O2 minus. So here nitrogen having 1 lone pair of electron, oxygen having 1 lone pair of electron. So either nitrogen donates or oxygen donates. Okay, most probably nitrogen donates because less electronegativity. Which one having less electronegativity, so that will more preferable to donate its lone pair of electrons. If it is having more electronegativity, it is not. It is always accept electrons rather than donation because of its high electronegativity. So what is electronegativity? Tendency to accept electron pairs, right? If in case oxygen donates its lone pair of electron, oxygen is donates its lone pair of electrons to the central atom and forming coordinate bond. So that is nitrito. It can be written as ONO minus, right? Here nitrogen donates its lone pair of electrons to the central atom. nitrogen donates to lone pair of electrons central atom, that is written as NO2 minus, and it is called as nitro in the nomenclature. Just write nitro. If oxygen donates its lone pair of electrons to the central atom and forming coordinate bond with the metal atom, that is nitrito. It can be written as nitrito. Okay, so this is nitro and nitrato. Okay, so let's take another example, that is SCN minus. SCN minus, NCS minus, SCN minus and NCS minus, SCN minus, NCS minus. So if sulfur donates, here sulfur and nitrogen both are having lone pair of electrons. Both are having lone pair of electrons at a time, either sulfur donates or nitrogen donates. If sulfur coordinates with the metal atom and forming coordinate bond with the metal atom, right? So that can be written as SCN minus, and it is called as thiocyano. Okay, thiocyano. If nitrogen donates its lone pair of electrons to the central atom and forming coordinate bond with the metal atom, that is this can be written as NCS minus, and it is called as isothiocyanate. Isothiocyanate, right? So these are the few examples for amber-dentate ligands. Right. So next, IUPAC nomenclature. So IUPAC nomenclature for coordination compounds, right? So they are here having certain rules to assign IUPAC nomenclature for a certain coordination compound, right? The first rule number 1, positive part of coordination compound should be named first. Positive part of coordination compound. So positive part of coordination compound should be named first. So name it first. Okay. So any compound which contains cation and anion. So every compound which contains a cation and anion. So whatever it is in left hand side, that is your cation. Whatever it is in right hand side, so that is your anion. So left hand side part is positive part, that is cation. Right hand side part is anion, that is anionic ligand, that is called anion, right? Cation and anion, positive part, negative part. So in coordination compounds, so which contains two parts, either positive part and negative part. So positive part should be named first. Okay, so either it is a complex compound or simple ion. The first preference goes to cation. Should name cation, like NaCl, sodium chloride, Na plus Cl minus. So it can be written as sodium chloride. So first name sodium, Na plus. So sodium chloride, right? And next, that is first rule. So cations name first. Second thing, if your positive part is your coordination compound, coordination sphere. So in the coordination sphere you are having a metal ligand. In the coordination sphere you are having a metal and ligand. So what is the necessary condition here? Metal having, so metal should have vacant orbitals, ligand should have lone pair of electrons. So ligands donating its lone pair of electrons to the central atom and forming coordinate bond, which is in the coordination sphere, right? So that part will not get ionized, because in aqueous solution coordination bond will never break. That's why it is not ionized, right? Next, so ligands. So in the coordination sphere you are having metal ligand. So which one gives first preference? First ligand. So ligands of coordination sphere should be named first. Okay, so ligands should be named first. So ligands could be anionic, cationic, or neutral. Okay, so ligands should be named first. Then after metal, right? So if in ligands, rule number 3. So what is rule number 3? If you are having repetition of ligands, so repetition of ligands. For example, if you are having 4, 5, 6 having same ligands, 4 ligands, 5 ligands. If if you are having two ligands, the complex should be linear. So, two ligands which are coordinated with the metal atom, that is linear. So, coordination number is 2. If you are having 3 monodendral ligands, coordination number 3. Okay. If you are having 4 monodendral ligands coordinated with the metal atom, the coordination number will be 4, right? If you are having 5 ligands, 5 monodendral ligands, so the coordination number will be 5. If you are having 6 ligands, the coordination number will be 6, right? So, for repetition of ligands, use prefix di, tri, tetra, okay, penta, hexa. If you are having 2, so the prefix is di. If you are having 2 ligands, the prefix is di. If you are having 3 monodendral ligands, use prefix tri. If you are having 4 monodendral ligands, use prefix tetra. If you are having 5 monodendral ligands, use prefix penta. If you are having 6 monodendral ligands, use prefix hexa, right? If you are having polydendral ligands, if you are having polydendral ligands in the complex, you are having polydendral ligands, then use bis. If you are having 2 polydendral ligands, for example, taking ethylene diamine, which already contains di, ethylene diamine, which is ethylene diamine. So, you should not use again di. If you are having 2 ethylene diamines in your complex, you should not use again di. You just use bis. For polydendral ligands, use prefix bis. So, these prefixes for monodendral ligands and these prefixes for polydendral ligands, that means bidentate, tridentate, tetradentate ligands. So, bis, tris, tetrakis, so pentakis, etc. Okay. In your complex, if you are having a bidental ligands, use prefixes. If you are having 2, you use prefix bis. If you are having 3, so use prefix tris. If you are having 4, use prefix tetrakis, right? So, that is rule number 3. Next, rule number 4. So, what is rule number 4? So, if you are having more than one type of ligand, then preference give according to their alphabetical order. Preference give according to alphabetical order. Preference give according to alphabetical order. So, if you for example, if you are having 3 different ligands, if you are having cobalt, H2O and Cl. So, which one name first? Which one give preference first? So, chloro starting with C, H2O aqua starting with A, chloro starting with C, H2O starting with A. So, first you should write H2O. So, aqua, then after chloride. Okay. So, in your complex, if you are having H2O and chloride, so chloride, if you are having 2 chloride atoms, chloride ions and 3 H2O, 3 NH3 molecules, then which one comes first, NH3 or chloride? So, if you just check alphabetical order, first alphabet. So, aqua, if first alphabet is the same, you just go to preference next alphabet, right? So, aqua, A, right, amine, NH3, amine, A starting with A, and what is next one? Chloride, right? Chloride starting with C. So, A comes first. So, should give first, should write amine, then after chloride, and the prefixes like di, tri. So, you should not consider the alphabetical order for these numbers. Okay, should not consider alphabetical order for these numbers. Should consider only ligands only. If you are having 2 ammonia, so you should not consider di, alphabetical order D. You just consider alphabetical order A, right? A. Just compare that alphabetical order of ligand. You should not consider number. Should not consider. So, consider taken into the numbers, right? So, that is rule number 4. Next, so up to this, so what is rule number 1? Positive part of coordination compound should be named first, and the second, if your complex ion having complex ion contains metal and ligand, so which one gives preference first? Ligand gives preference first. Next, for repetition of ligand, if you are having more number of ligands, use prefix di, tri, tetra, and for bidental, tridental, tetradental ligands, use prefix bis, tris, tetragas. If you are having more than one type of ligand, use alphabetical order, right? And the next, so after so giving name to the ligand, you just give name for a center metal atom. central metal atom. So central metal atom name should be named followed by oxidation state, followed by oxidation state within the bracket, this kind of bracket, that is parenthesis. Should mention oxidation state of central metal atom in this kind of bracket, right? So that is fifth rule. You just calculate here oxidation state. So how can you? So how would you calculate oxidation state? I will explain. Don't worry about that, right? So that is rule number 5. And next, after central metal atom, so here complex compound. So the coordination sphere name will complete. Was complete. Next, which is the ion which is outer sphere, that is the ionization sphere, name first. Next, out of the coordination, the ion. So the after metal, the anion which is in outer sphere. So outer sphere or ionization sphere should be named. Okay. Next, so after completion of after giving the name for a coordination sphere, and the next, out of this coordination sphere you are having if you are having a negative charge ligands, so that is which is in outer sphere, that is ionization sphere, then give the name. And one more thing here you have to keep in mind, if you are having three chloride atoms in coordination in ionization sphere, out of this coordination sphere, if you are having three chlorides which is in outer sphere, that is ionization sphere, you should not mention that number. You just should not write trichloride, you should write just chloride, right? And if a metal atom, so while naming the central metal atom, if you are having over the coordination sphere, if you are having positive charge or no charge, that is neutral, the metal name, that means the metal name as it is, the metal name as it is. For example, if you are having cobalt, over the coordination sphere, if you are having positive charge, you just the name of this central metal atom is just cobalt. You just write cobalt. After that, you should calculate the oxidation state and write in the this kind of bracket, that is parenthesis, in Roman numbers. If you are having a negative charge over the coordination sphere, if you are having negative charge over the coordination sphere, the metal name ending with 8, the metal name ending with 8. If you are having cobalt over the coordination sphere, if you are having negative charge, that is cobaltate. If you are having iron, so that means ferrate, Fe, ferrate. Okay, chromium, chromate. Okay, so whatever it is. So in central atom, if you are having negative charge over the coordination sphere, the metal name ending with 8. So this thing you have to keep in mind, right? And the last one. So if you are having more than one type of metal, if you are having more than one ligand, so those two metal in the coordination sphere, if you are having more than one metal, so those two metal atoms are joined with ligands. Those ligands are called bridging ligands. Those ligands are called bridging ligands. So while naming the bridging ligands, use prefix mu. So this mu indicates that ligand which is acts as bridging between those metal atoms, right? So that is rule number 7, last rule. Okay. So these are the few rules you just have to remember. So while naming the coordination compounds. Okay. So now let's forward with the examples. At first example, CONH3 6 times Cl3, right? So this part is ionization sphere, this is coordination sphere. So this is coordination sphere, this is ionization sphere. This part will get ionized. So this complex compound which gives how many ions in the solution? CONH 6 times 3 plus CONH3 6 times 3 plus and 3 Cl minus. How many ions here? 1 plus 1 cation. Your cation is complex ion. Your complex ion is cation. So cation may be cationic, anionic or neutral. If you are having over the coordination sphere, if you are having positive charge, so that is your cationic complex ion. If you are having negative charge, that is your anionic complex ion. If you are not having any charge over the molecule, that is neutral complex compound, right? So here 3 ions. Now first here the left hand side, that is always cation, right hand side, that is anion. Now the first rule is cation part should be named first, that is this part. So this part which contains the metal and a ligand. So coordination number is here 6. Coordination number is here 6. Right. Now 6 ammonias donating their lone pair of electrons. Ammonia over the nitrogen, here having lone pair of electron, their lone pair of electrons donated to the central atom and forming coordinator bond. Okay. Now here metal atom, central atom. The second rule, that is ligands of the coordination sphere. In the coordination sphere, ligands should be named first. Give the preference for ligands. Here how many ligands we are having here? 6. For repetition of ligands, rule number 3, for repetition of ligands you use prefix di, tri, tetra, hexa, hepta, right? If we here having 6, so use prefix hexa. Okay, the name is hexa. NH3 is neutral ligand, that is amine, hexaamine. And next after giving the name to this ligand, next central atom, that is cobalt. So here over the coordination sphere having positive charge. So over the coordination sphere you are having positive charge. So their metal name as it is, right? If you are having negative charge, metal name ending with 8. Okay, here you are having positive charge. So cobalt followed by oxygen state which is mentioned in this kind of bracket, right? So parenthesis. Now how to calculate oxygen state for this complex, right? So for that this is complex ion now, that is cationic complex ion. You don't know oxygen state of cobalt here, just let's say X plus so 6 ammonia ligands, right? 6 into, so each ammonia donates its lone pair of electrons to the central atom, and over the ammonia you are not having any charge. So this ammonia is a neutral ligand. So that means the charge that's why this ammonia is a ligand considered as neutral molecule. So here it is 0. 6 into ammonia having no any charge, not having any charge. That is equal to that would be equal to the charge over the coordination sphere. The charge over the coordination sphere, that is plus 3. So X comes out to be 3, plus 3. So the oxygen state of cobalt here plus 3. Okay, right? I repeat it again. So cobalt oxygen state of, so in order to calculate the oxygen state of cobalt here, you should know the nature of ligand here. Okay, either cation ligand or anion ligand or neutral ligand. Here ammonia is neutral ligand, so that means no charge over the molecule. So here 6 into 0 equal to, which is equal to the charge over the coordination sphere. Here charge is plus 3, so X equal to plus 3. Just write in Roman numbers 1, 2, 3. Okay, so hexaamine, cobalt 3. So next after the coordination sphere, the ligand, the ions which are in ionization sphere, that is Cl. So here just write chloride, not trichloride. You need not to mention this number. Okay, chloride. Okay, got it? Right. So let's take another example. So K4FeCN6. K4FeCN6. Right. Now, so this complex can be dissociated as, so this part will not get ionized because this is coordination sphere, complex ion will not get ionized. So this part will get ionized, that is this can be ionized as 4K plus FeCN6. Here 4K plus 4 positive charges, 4K plus, so this can be balanced by 4 negative charges here. This means this can be ionized as 4K plus and FeCN6 4 minus, right? Now here potassium is your cation and FeCN6 4 minus, so that is anion. Here the complex ion is, the complex is anionic complex because over the coordination sphere here you are having a negative charge. So this is anionic complex, anionic ligand, right? Here ligand also anion ligand, right? So now starting with cation, that is potassium. Just write potassium, not tetra potassium. This number, the ion which is whatever it is which is present in ionization sphere, you need not to mention this number. You just write simple potassium, right? So potassium. Next, coming to coordination sphere. In the coordination sphere, metal, you are having metal and ligand. So just give reference to first ligand, that is hexacyano. So potassium, hexa, so Cn. So the over the cyanide you are having negative charge, that is anionic ligand, negative ligand, that is cyano. Ending with O, cyano, hexa 6, hexa cyano, and here Fe over the oxygen state. So over the coordination sphere you are having negative charge. So the metal name ending with 8. So hexacyano ferrate. Okay, ferrate, oxygen state of iron here. So how can you calculate oxygen state of iron here? So just let's say X. You don't know oxygen state of metal here. Just say X plus cyanide. 6 into over the cyanide you are having negative charge. So 6 into, so 6 cyanides, 6 cyanides having 6 minus ions. That means 6 into minus 1. That is equal to the charge over the coordination sphere. Over the coordination sphere having negative charge, that is minus 4. So X comes out to be 6 minus 4, that is plus 2. Okay, the oxygen state of iron here plus 2. So which is written in Roman numbers within this kind of bracket, that is parenthesis. And next, potassium hexacyano ferrate 3, or you can write iron 3, right? So next, let's take an example for a neutral complex NiCO4. So this is over the coordination sphere, you are not having any charge. So this complex is neutral complex. So here within the coordination sphere, you are having a carbonyl and a nickel, right? So first starting with ligands. So how many ligands here we are having? 4. So tetracarbonyl nickel. So over the coordination sphere you are having 0. So the metal name as it is, that is nickel. So tetracarbonyl nickel. Within the brackets, the oxygen state of nickel here. So X plus carbonyl is neutral ligand. Over the carbonyl, over the CO, you are having 0, no charge here. Okay, so that means this is your neutral molecule, neutral ligand. That's 4 into 0, which is equal to the charge over the coordination sphere. That is also 0. So X is 0. So coordination oxygen number is 0. Just mention 0. So tetracarbonyl nickel 0, right? If you are having NiCl4 2 minus, so this is anionic complex, this is ion. Okay, so anionic complex here, tetrachloro nickelate. Here over the coordination sphere we are having negative charge. Over the coordination sphere we are having negative charge. So the metal name ending with 8. So tetrachloronickelate, oxygen state of nickel here. So X plus, you don't know oxygen state of nickel here, just say X plus. Now each chlorine having 1 negative charge. Over the chlorine you are having negative charge. So X plus 4 into minus 1, that equal to the charge over the coordination sphere, that is minus 2. So X comes out to be 4 minus 2, that is 2. The oxygen state of nickel here 2. So tetrachloronickelate 2, and this is ion. You should mention ion because this is in ionic form. Over the coordination sphere having charge. So this is ion. Just mention ion. So tetrachloronickelate 2 ion. Okay. Next, complex CONH3 twice CO twice Cl2. Over the coordination sphere having charge plus 3, right? So CONH3 twice, CO twice, Cl twice, right? So you are having 3 different ligands. So one is amine, carbonyl, carbonyl and chloro. So first the rule number 4, if you are having more than one type of ligand, the preference give according to the alphabetical order. So amine, okay, starting with A, carbonyl starting with C, chloro starting with C. So here amine starting with the A. So this ligand comes first. That means diamine next these two. This is carbonyl, this is chloro. Both are starting with C, and the next letter carbonyl Ca, and this is chloro Ch. So A comes first. So carbonyl. So diamine, dicarbonyl, dichloro. Next dichloro. Next cobalt. Over the coordination we are having a positive charge. Just write cobalt. And followed by oxygen state of cobalt here. So just let's say X plus 2 into ammonia is 0, neutral molecule. Carbon also 0. Plus chlorine, each chlorine having 1 negative charge. Here 2 chlorines, 2 negative charges. 2 into minus 1 over the coordinates we are having positive charge, plus 1. So X equal to 2 plus 1, that is plus 3. X comes out to be plus 3. Cobalt oxygen state here 3. This is written in Roman numbers, right? So diamine, dicarbonate, dichloro, okay, dichloro, and this is ion. Over the coordinate sphere you are having positive charge. So just mention ion. Okay, right. If the complex having bidentate ligands, in that case CO En twice Cl2 plus. So name this complex. First ethylene diamine. Here two types of ligands. Here chloride is a monodentate ligand which donates one lone pair of electrons to the central atom. Here ethylene diamine is bidentate ligand. Bidentate ligands. For bidentate ligand use prefix bis. If here you are having two ligands now, so use prefix bis. So bis ethylene diamine. Here it is dichloro. So which one comes first? Ethylene diamine starting with E, chloro with starting with C. So C comes first. So dichloro. So dichloro bis, dichloro bis, within the brackets write the name of this bidentate ligand, that is ethylene diamine. So dichloro bis ethylene diamine and cobalt. So over the coordinates we are having positive charge. So just write cobalt oxygen state here. Ethylene diamine is neutral ligand. So X plus 2 into neutral bidentate ligand, 2 into 0 plus 2 into chlorine is minus 1. 2 into minus 1 equal to overall charge plus 1. So X comes out to be plus 3. Cobalt oxygen state here 3. And it is over the coordinates we are having positive charge, that is cationic complex. So this is cation, you just mention ion. Okay, so dichloro bis ethylene diamine cobalt 3 ion. Okay, you just write all these things. Right. Last example I take which right. Let's take bridging complexes. Right. FeOH NH2 Fe. Let's take NH3 4 times, H2O 4 times, SO4. So over the coordination sphere here having here two irons, the complex which contains two metal atoms, two ligands which are bridged with these two metal atoms. OH acts as bridging ligands which connects these two metal atoms. NH2, that is amido, NH2 minus. Here it is anion ligand, OH minus, NH2 minus. These two are the bridging ligands. So when naming the bridging ligands, use prefix mu. Remember last rule, mu. Use prefix mu hydroxo, mu amido. Right. Now here starting with amine or aqua. So here over the coordinate sphere here minus 2, here it is 2 plus. First you should calculate oxygen state of iron here. If you calculate oxygen state of iron here, here 2 irons na, 2 irons. So 2x plus OH minus, minus 1 and H2 minus, that is minus 1, which is minus 1 minus 1 and which is equal to plus 2. So 2x equal to minus 1 minus 2, that is 4x equal to plus 2. The oxygen state of iron here plus 2. Oxygen state of iron here plus 2. Okay, so just write tetra aqua tetraaqua iron 2 tetraaqua iron 2 mu hydroxo mu amido mu hydroxo again iron tetraamine iron 2 sulfate. Okay, right. So you just use your mu hydroxo mu amido mu hydroxo mu amido, right. So in this way you can try your own examples. Okay, so as many complexes as you can, so that your confidence will increase. So definitely if everything is clear in your mind, if you know all the rules, okay, so none of the question will get wrong in the examination.